Dear Rector, dear Deputy Minister, dear colleagues, dear guests, and generally dear friends, welcome at the 32nd International Scientific Conference Electronics 2023. My name is Petar Yakimov, and as a Scientific Secretary of the conference, I have the pleasure to congratulate you at our conference. In these 32 years, we have built a very strong community which is gathering here every year to exchange ideas, to exchange impressions, and of course to have a pleasant time at this magnificent place, the ancient Apollonia, according to me, the best and the most beautiful place at the Bulgarian seaside. First, I would like to thank all institutions and persons who contributed to the successful organization. They are the Research and Development Sector of the Technical University of Sofia, the Faculty of Electronic Engineering and Technologies, and personally, Росен Радонов, Димитър Николов, Борислав Ганев, Ивелина Рускова, Светомир Лазаров, Николай Хинов, Пламен Аврамов, and all who I have missed have to excuse me. For this conference, I have been thinking in the last time, and I can express my opinion that the conference is useful because attending a scientific juries for approving scientific degrees and academic positions, I see many publications of the applicants that are presented at our conference. Also, in this year, I can see many young and already not too young colleagues, which careers have grown up in very close connection to the conference. They started their participation as PhD students, after that as PhD holders, and by now some of them are themselves PhD supervisors. So this is a tradition that I think will continue in the years. But I think also that it's time some of them to take my place in very close time. I would like to congratulate our invited speakers, Professor Valery Mladenov and Professor Evtim Peichev, have decided to attend our conference at last at the 32nd issue. Although they are very close friends of us, they didn't attend our conference, but I hope that they will evaluate what they have missed and will promote and advertise our conference among their colleagues. So after this introduction, I'm giving the floor to Professor Ivan Kralov, Rector of the Technical University of Sofia and Honorary Chair of the Conference, for the official opening. Professor Kralov, please.
Dear organizers, dear participants, dear guests, it is my great pleasure to welcome you here on the behalf of academic management of the university, on the behalf of me, I wish you good health and fruitful participation in this event. About 8 years, Technical University of Sofia is not only a leading technical university in the region, but it states the standards for higher education and research in the technical areas. You know our famous framework, Days of Science of the Technical University of Sofia. They cover more than 30 conferences organized or co-organized by the leading research teams in our university, and they are like a stamp for quality in research in Bulgaria. So warm thanks to all of you, the organizers, the participants, guests and sponsors, and I'm really inspired of the presence of young people. They prove the sustainability of our work, and they make us happy. They prove that we are working in a right way. But also, this interdisciplinary character of research works, of course, high level of research works, and the opinion in our industry, in our society, prove that we could help and could transfer the knowledge, the science, the technologies from the academia to the industry, to the business, to the society. And this is the most important thing. You know, last week I have signed the agreement between our university and the leading Greek technical university, and there at Thessaloniki, Greece, at the International Fair, where we have a pavilion for education, I have some conversations with our ministries, and they are convinced that the right place for future education and development of the microelectronics as a high level of education is Technical University of Sofia. Of course, some of the flows for this future development of the research work between our and Greek universities is in the area of microelectronics, in the automotive electronics, and of course a lot of very close specialties. So this proves that we work very good with the industry, very good with the government to fulfill the requirements of the industry. I wish you to have a fruitful participation here and also to enjoy the beauty of the ancient and modern town of Sozopol. Good luck and thank you.
Now for greetings, the floor is given to Professor Георги Ангелов on behalf of the Ministry of Innovation and Growth.
Thank you very much, dear guests, dear rector, dear colleagues. It's my pleasure to open this conference on the behalf of Ministry of Innovation and Growth and the Minister Milena Stojcheva, also my personal behalf. It's a pleasure that our conference is already more than 30 years and it sets the standards for our local and regional community in electronics and all its applications. I will say a few, let's say, known information and some new information. The Ministry of Innovation and Growth, you know, is established around 2 years ago, and the most important tasks in this ministry are to promote the innovations based on research and development, and this is one of our priority of the current ministry and the leading team to expand the innovations in Bulgaria, but these innovations that originate on research and development efforts, these are the universities, and especially in electronics, microelectronics, automotive electronics, these are the leading areas in the upcoming, maybe these are expected to be the leading areas in the upcoming 30-40 years. So currently there are a lot of instruments that, how to say, in practice can promote such developments in the form of projects. We have started in the end of June the so-called circular economy procedure call for projects. This is within the framework of the Recovery and Resilience Plan. It is 180 million leva and it will be opened until the 3rd of October. These are all the activities related to reducing the footprint of carbon and wastes, so this requires a lot of engineering. Also are expected to open very soon two closely related to our profile procedures. They are with a part of the new program called in Bulgarian PNIDI. This is the research innovation and smart and digitalization for smart transformation. We expect there to one for implementation of innovations and the other is for development of innovations. There are expected to have a lot of interactions between the industry and the academia with experts such as our profiles. And also very important is that now we are in process of including Bulgaria in the so-called Key Digital Technologies Joint Undertaking. This is expected to transform to CHIPS Joint Undertaking, which will invest, the EU CHIPS Act last year was set on the table and in July it was adopted at European level. So now in October, this Key Digital Technology Joint Undertaking will become CHIPS Joint Undertaking. These joint undertakings are formations of the Commission that fund projects closely related to the market, technology readiness level 6, 7, 8. Because Europe, one of the main drawbacks of Europe is that the research is a bit more scientific and abstract, not so close to the market as it is in the, let's say, the United States and in Asia. So these joint undertakings intend to invest in projects that originate from collaboration between the industry and academia. This will give us opportunity for large-scale projects and especially centers of competence in microelectronics and related areas. We have a lot of opportunities within the European University of Technology framework. You know that it finished this year and now we are about to go in the second phase for the next 4 years. So we have a good framework with partners within the university, also good framework with industrial partners. We plan next week to go in the United States and we will sign a memorandum of understanding between Bulgaria and the United States, and there will be a special part related to innovations, and there we will cover emerging technologies. These are the artificial intelligence, all Internet of Things applications, microelectronics, information technologies. So here the colleagues, especially the young one, have to be ready for a lot of new challenges in the upcoming years that will be funded and will be at European and world level. So wish you success. Thank you.
Thank you, Professor Angel. Now, on behalf of the organizing committee, the floor is given to Professor Стоян Нихтянов from Delft University of Technology, General Co-Chair of the conference.
So, dear colleagues, I want to join the previous speakers here, the rector and deputy minister, I understood, to welcome you to this 32nd edition of electronics, also on behalf of the Technical University in Delft, the Netherlands. Maybe you don't know, all of you, that since 1995 this conference is co-organized by TU Sofia and TU Delft. TU Delft has been presented some years with more people, other years like this year not so many people, but this tradition goes on and I hope it will continue in the future. So 32 years is quite a long period of time. Electronics has taken place in good years, but also in not so good years. This year is very special, it's very dynamic, I would say even dramatic. A lot of things happening around us. Mother Nature shows its strength. Even recently, a few kilometers to the south from here, there was a flood with, unfortunately, some victims. But what to say about the flood in Libya. A few thousand people perished because of flood, earthquake in Morocco. So things are happening. And the reason is that probably we do not respect nature enough. Of course, there are also other dramatic events happening here in the Black Sea, which we have to be more, let's say, proactive and to think how we can stop these events or prevent in the future this to happen. And science is one of the means, actually the most important means to do this. And conferences is the place where we exchange knowledge, information, we create new links, and that's actually the most important aspect of a conference. Years back, somebody asked me when a conference starts. So it's a very interesting question, when a conference starts. And I was thinking a lot of time after that, I came to the conclusion that some conferences, they take place, but they do not start, actually. They do not start because the goal of the conference is, I already mentioned, to present new knowledge, new information, to exchange information, and this information to be spread around. And if this does not happen, the conference actually does not start. And there are other conferences which start much earlier before they take place and continue longer after they finish, because the news of something great has been announced during the conference, of course, is remembered for a long time. So I wish this conference belongs to the conferences which really start and never end through the years. And I wish you success and also enjoying your stay, your time here. Thank you.
And after the greetings, we proceed with the plenary session. There will be presented two invited lectures. The first is entitled The Fourth Element of the Rediscovered Memristor. It will be given by Professor Валерий Младенов from Technical University of Sofia, and let me introduce him very briefly because he is well known. Валерий Младенов received his PhD from the Technical University of Sofia in 1993. In 2019, he defenses a Doctor of Science thesis at the same institution. In 2004, he becomes the head of the Department Fundamentals of Electrical Engineering. Since June 2011, he was a Dean of Faculty of Automatics. Since December 2011, he has been a Vice Rector of Technical University of Sofia. Currently, he is head of the Department of Fundamentals of Electrical Engineering and head of the Neural Computing Laboratory of Technical University Sofia. He is a guest lecturer at the Faculty of Electrical Engineering, Eindhoven University of Technology in the Netherlands, and many others. Professor Mladenov's research interests are in the field of electrical engineering, artificial intelligence, power systems, electronics, neural networks. He has received many international research fellowships. He has more than 350 scientific papers in professional journals and conferences. He is a co-author of 20 books and manuals for students. He had received many research grants, and also with his team he participated in many national and international projects. Horizon 2020, FP7, Royal Society, DFG, NWO, Erasmus Plus, and others. As a member of several editorial boards, Professor Mladenov serves as an editor-in-chief, associate editor, and reviewer for a number of professional journals and conferences. He is a senior member of IEEE, a member of the IEEE Circuit and Systems Technical Committee on Cellular Network, Nonlinear Networks, and Memristor Array Computer, and an Educational Activities Officer of the Bulgarian IEEE Section. He is also a senior member of the International Neural Network Society, member of the International Council of Large Electric Systems, member of the Steering Committee of the International Symposium on Theoretical Electrical Engineering, member of the Management Boards of the Scientific and Technical Union of the Power Engineers and the Union of Automation and Informatics in Bulgaria. So, Professor Mladenov, you have the floor.
Thank you very much, Mr. Secretary, for this extended introduction. I wrote all these texts, but you read it, everything. And maybe it's a for the audience. So, dear Mr. Rector, dear Mr. Deputy Minister, dear organizers, dear colleagues and friends. First of all, I'd like to thanks for the organizers for inviting me to give this invited talk. My name is Valery Mladenov, and at the moment I come from the Department of Fundamentals of Electrical Engineering, and this is very close to electronics. In fact, my department teaches students on the Faculty of Electronics on the fundamentals of circuits. So my research activities are very close to the area of electronics. The outline of my presentation will be as follows. First, I'll give some introduction to memristors. This is mainly part that will be common. And then I'll try to talk about memristor modeling and applications. Especially I'll focus on the things that my group is doing. The talk is about memristors, and I'm starting with this well-known picture. You know the four basic electric quantities: voltage, current, electric charge, and flux linkage. Simply called flux. All these connections are known. Flux is time integral of voltage. Charge is time integral of currents. The connection between voltage and charge is a well-known capacitor. Developed 1745 von Kleist. Voltage current relation is presented by element resistor, presented 1827 by Ohm. Inductor flux relation is current flux relation is presented as inductor, well-known relation, developed presented by Faraday 1831. So only this link between flux linkage and electric charge is missing. For the sake of symmetry, you know the universe, everything is symmetric, something should be here. And you see we have three main electric circuit elements: resistor, inductor, and capacitor. This link is filled by the famous paper Chua in 1971, this one. That time Chua was 35 years old and started to develop the fundamentals of circuit formal circuit theory. That time he first predicted theoretically existence of memristors, presented a lot of equivalent schematics, but you know, resistor, inductor, and capacitor you can meet everywhere. Resistor is a piece of wire, inductor is turned wire, capacitor two conductors with insulator. But such simple realization of memristors since 2008 does not exist. And because of this element somehow was neglected. Even 1971 was developed, but there was no circuit element, two terminal, that represent this connection between flux and charge. But in 2008, famous paper in Nature by the team of Hewlett-Packard showed that device, very simple device, could obey memristor properties. And this is the beginning of the new era of memristors, 2008, when the research started and many type of memristors, two memristors were developed. A lot of research, a lot of useful properties of memristors have been shown. So, this is Chua. He is on 87 now, still in good condition, working. This is Chua. Memristor is an acronym for memory resistor. Now I'm going to simply explain the principle of working of the Hewlett-Packard. This is titanium dioxide memristor, to see why it is memory resistor. This is the electric symbol of memristor. What we have here, two platinum electrodes and titanium area divided in two areas, doped and undoped titanium dioxide area. So here we have positive charges, extra positive charges. The width of the doped layer is W, the total area is D, State variable is ratio omega over D. If we, this is two terminals are called anode and cathode. If we supply electric field or supply voltage shocks with this direction plus minus, this boundary starts to move to right, extend the doped region, and at the final moment when X became D, all area is conductive, so the resistance became zero. So this became R on. When we supply opposite voltage, the area starts to be shrink to here, and the resistance of this became R off. So this middle state of the boundary determines the number of charges, and this number of charges, in fact, is determine the current that flows through the memristor. And this depends on the path. This depends on the path because relation flux I'll show charge. Flux and charge are integral characteristics. So the information in there, in flux and charge, depends on the path. So memristor depends on the path. Memristor by definition is derivative of voltage with respect to current. If we take into account that the voltage is rate of change of flux, current is rate of change of charge, you see the memristor is rate of change is the rate of the derivative of flux with respect to charge. See the picture. If this is the charge flux, what we have flux charge characteristic, flux charge characteristic. The memristor is the slope of this curve. So if this is the flux charge characteristic, this is the memristor. Voltage is time derivative of the flux. It became memristor multiplied by current. Memristor depends on charge, and because of this is the memory effect that comes from charge, who at any instant could be different. And I forgot to mention, if we remove the supply here, this structure stays in the last state that we live in. So the resistance is remembered. The resistance is remembered. So this is the memory depends on the charge that is at the moment. The opposite of the resistance, the opposite is called memductance. Like conductance is for resistor, memductance. The unit of memristor is volt, is ohm. So it's measured with the same unit as the resistor. But this is memory, so memory depends on charge. The idle memristor obeys these equations. Voltage current relation is through memristor, and the current is the rate of change of the charge is the current. Idle memristor because we do not restrict the charge. For generic memristor, this is more extended equation. In fact, charge is proportional to the state variable. Remember, state variable was the width of the dot region over the total width. So it depends on charge. So it's proportional. State variable is proportional to the charge. And here, generally, is the function depends on charge and current. If we supply here, sine wave voltage, the idea is to obtain the volt ampere characteristic of the resistor. In time, we change simply change the voltage with given frequency. This is the characteristic that we got. The fingerprint of characteristics pitched hysteresis loop. And for different frequencies, so if we increase the frequencies, the area of the loops became smaller and smaller, shrink. And in fact, this also is confirmed by the theory that increasing the flux, the area of the current voltage hysteresis loop is shrinking. I will stress on these properties. About DC high curve, memory switching properties, operating modes, activation thresholds, passivity and nonlinearity. These are things that I'm going to talk in the first 1/3 of my presentation. Suppose we have a resistor and this is DC voltage, continuous in time, to measure the DC volt ampere characteristic. What will happen? This volt ampere characteristic consists only of one point at zero. So why? Because if we continue to keep the voltage, what will happen? The resistor will melt. We do not. Why? This is very, very simple, because the flux is integral voltage, and if the voltage is constant in time flows, this is the, so we have constant at zero plus this constant multiplied by t. If, for example, the relation is charge is power cubic power 3 of the flux, then we got this value for current. So it's on power 2. You see, in time, current will rise continuously. This will lead to melting the membrane. So at DC voltage, we never put membrane to DC voltage. DC characteristic is only one this point. If charge flux relationship is piecewise linear, at every linear part, you know the membrane resistance is derivative of flux with respect to charge. So this is the constant, constant, constant. So at these points, we have different membranes. This simply confirms that membrane could switch between different membranes could switch between different points at these points, between different values at these points. Now, about memory and switching properties. Switching is very important because, you know, we use transistor in electronics to switch around and off. Membristors could do this. I show you that only for the titanium dioxide memristor, his resistance could switch from on to off. Here it is illustrated with voltage pulses between 0 and 1. What we are doing, if voltage stays at level 0, boundaries should move and the resistance should start to decrease. The states start to increase. At this place, when the value is 0, then the resistance stay constant. So the resistance stay constant, stay variable, stay constant. So if we supply chain of pulses, state variable should move from 0 to 1, the resistance should move from R on to R off. Sorry, from R off to R on. If the pulses are between 1 and minus 1, the resistance at 1 is 0. So when we have voltage level 1, the bulb base is the right side. If the pulse is 0, the membristance is error. So with these pulses, we show the switching of the memristor switching properties of the memristor. This is the state variable. There are two switching modes. The first is called soft switching mode. The second is hard switching mode. Soft switching mode is when the state variable does not reach the final points -1 and 1. Current voltage relationship is this pitch hysteresis loop. It is and this is the state flux leakage characteristic is single value. This is the state flux characteristic. This is volt amp characteristic. State variable does not reach -1 and 1. In hard switching mode, state variable reaches 1 and -1 and could stay there. Then the volt amp characteristic is non-symmetrical curve like this, and flux charge characteristic is multivalued like this. In hard switching mode, there are some interesting properties. When we reach 1 and continue to increase the voltage, states continue to stay 1. And then, in the moment when we the voltage start to decrease, state immediately start to decrease from 1. So state somehow is stick at 1, and then on 0 when we are on the opposite side, in the hard switching mode. The important for membristors is activation threshold. This is a level of voltage below which membristance does not change. So the charge stays the same as it is. And below the activation mode, memristor works as normal linear resistor. Above the activation mode, it works like memristor with this switching and memory properties. You see, if the voltage is below the activation mode, state variable stays constant. It works like resistor. The memristor is strictly passive element. You see, volt amp characteristic is the first and third quadrant. In contrast to the inductor and capacitor, memristor could not store electric energy. You know, inductor store magnetic energy, capacitor store electric energy. Memristor could not store energy. However, the memristor could store information as a form of its membristance and charge. And the last property that I would like to talk is nonlinearity. You see, memristor is nonlinear because the characteristic flux charge is nonlinear. So if the voltage is sine wave, current is not sine wave, and this is the corresponding, as we discussed, current voltage relationship. Some potential applications of memristors. Two most important potential applications are in neural networks and in memories. Why in neural networks? Because you know the connection between axon and dendrite, axon of one neuron, dendrite of the other, is synapse, side synapse. Everybody know from neural network what means synapse. Memristor behaves like the synapse because memristors change proportional to the voltage pulses because it's integral of voltage. Synaptic connection changes proportional to the amplitude and time of nerve pulses. So this similarity makes possible to model the synapse in neural networks with memristors. And what about the memories? I forgot to tell in the beginning that nowadays dimensions of memristors about 8 nanometers. And the technology for metal oxide memristor, like titanium dioxide, is similar to semiconductor. So could be both technologies could be joined together on the same substrate. So memristors could be built together with semiconductor devices on the same chip. And this is the most important because a lot of schematics need not only memristors but also another electronic components, and they could be built on the same chip. So, about well-known USB memory, what the disadvantages? Could not scale the components below 20 nanometers. Comparatively poor retention time between 10 on 4, 10 on 5 times. Low switching speed, comparatively high power consumption. You know, problem with power consumption is very serious with all these semiconductor devices. What are the advantages of memristos? Then non-volatile nanosize. Non-volatile nanosize. Non-volatile, you know what means? They does not depend on energy. So when you remove the source, the memristor remembers this final state. So we can build non-volatile memories on nanosize. So these two main properties make it different between today's memories and Hewlett-Packard. Only in 2009, I read first, they promised to have memristor memories in 5 or 6 years. I guess they have now, but didn't publish commercial memory application. But what we expect in the future? Memristor memories to replace flash memory, DRAM, and hard drives. They're very, very, very appropriate to build memory. So neural networks and memories are the main applications for memristors, together with reconfigurable devices, because you know memristors can change, so you can get different devices based on this. Some types of memristors. Now I talk about metal oxide, but there are many devices have been developed with memristor properties. Polymeric memristors based on the electron spin, ferroelectric memristors, silicon-based memristors. And this also could be extended. I didn't put all this, I put this that I read for them, but many devices with memristor properties. About metal oxide memristors that we try to implement together with semiconductors, well known are titanium dioxide, cadmium oxide, tantalum oxide, vanadium oxide, niobium oxide memristors. All they have similar properties and could be built. Now I'm going to the second part about the modeling of memristors. This part I'll go to skip a little bit because this was my monography was written on this, and my second thesis for doctoral degree was based on this topic, about modeling of the memristors. And I start to work on memristors 2009. Since this paper in 2008 appears, since 2009 I start to work on this. And the things that I did on modeling and continue to do, the main things were before about 2019, about 2018, 2019. So my group, what we did is to did good models for memristors. Why? Because memristor is not simple elements like inductor, capacitor, and resistor. Needs more clever models. This model should be run on simulators, and every development, every small change is related to reducing the computational time. There are a lot of parameters that could be used for comparison to compare the models. Simply, you see the main equations: current voltage relationship from resistance and state and the rate of change of the state variable. These two equations will lead to all models. Here, in all equations, you see one parameter is called the window function. This function keeps the state in 0, 1. Because if we do not have such a function, the state could leave this, and this is not appropriate model. So a lot of models, this function is step function. This is continuous at point 0. What I did in many models was to replace this with sophisticated functions. I'll skip all these things because I see the time is running. I don't know how much time I have, but I guess
at least 40 minutes.
At least 40. Where I am now. Maybe at the middle, or I forgot to see.
You passed 15 minutes.
Oh,
15.
Fantastic, fantastic. All these models are mathematical models, so for many members took some of the corresponding papers. What I did in all this, for all these models, I made some improvement. Else, either in window function or in some parameters here that made the models simple. I gave a big list with references. What was one of the main things that we did to replace this function with analytical sigmoidal logarithmic sigmoidal function that is differentiable at this point, and during the simulation we do not have problems at this point because for this function, because first derivative here is infinite, infinite, so we could have problem at this point. So we express this function, this, or it looks like, or and the window function looks like this. What was the contribution of my group is that for first time we defined criteria for comparison of the models. When we read a lot of references, one author compared the models based on computing time and simplicity, another using another criteria. I tried to find out all possible criteria or develop new based on these criteria to compare the models. And what finally I obtained, signal levels at which memristor can work, non-linearity, expression of the boundary effects that I discussed in hard switching, representation of switching effects from R on, from R off to R on, model accuracy. This is the I get definition for all these things, for all these criteria. Activation threshold, model tunability, correct presentation of voltage dependence of nonlinear ionic dopant drift, ability to extract a symmetric voltage current characteristic, modes of operation, whether they could work in soft and hard or not, correct presentation of steady-state voltage characteristic, complexity of the model, operating frequency, because some models work at low, some high frequency. So in my monography, I tried for first to systemize, to find out all criteria for comparison, and did comparison of the models. Let's see, simply, I presented here only simply some known models and some altered models. And what we got is we reduce, in our models, we reduce the computing time and do not switching property. We keep the complexity. We reduce also the complexity. So this is my book, my monography, and all my things were connected to what good accuracy, close to one of the best model, low complexity, high operating frequencies, good switching properties, and reduce simulation time. All these efforts that were done in modeling were related to this. I'm not going to talk about modeling because it's a lot of mathematics and a little bit tedious to talk about mathematics here. But simply, I would like to mention what this mathematics is related to. What I would like to mention is that only one slide more, how to tune the models. We tune the models based on volt-amp characteristic and optimization procedure. So depending on parameters that we have in the model, in this equation, 3 parameters, we tune the parameters based on optimization procedure to track volt-amp characteristic with error up to 5%. So depending on the root mean square error, models has different complexity. But this is not the whole story. This is not the whole story. Models are useless if you do not implement them. What we did the Memristor library, and it is open in GitHub for all models, known and altered models. This is the address of where it is. This is the address of the GitHub. Symbol of Memristor. This is 2-terminal device. Sometimes we put 1 terminal from the state. We do not use it, but if you would like to measure the state variable, we have 1 more terminal. So we have complete library, and everybody could use it and implement it. Thanks to Professor Gajeva, who is expert in SPICE, she helped us to do all these things, to incorporate models into LT-SPICE, and there are a lot of explanation how people can download and to use them and to compare. So everything is one can prove by itself. So, but by himself to upload the model and to make the corresponding simulations. Now applications. I told them main applications are in memories, neural networks, and reconfigurable devices. Again, there are a lot of slides where we did a big review of papers where people presented this, especially for memories. However, we didn't find practical schematic, electronic schematic, and the corresponding model in simulator that show that we can compare the behavior of the memory, reading, writing effects, to compare different models. So what we did, we developed based on our library models, we tried to check behavior of the memory. If we do model with different models, the reading and writing effect in the Memristor memory. Crossbars of Memristors. A lot of work is done of Memristor logic gates. Again, I'm not going to in details, but the best papers are here. We also developed a gate. For example, this is ANT gate, and the corresponding LT-SPICE realization, and proof how it works, that everybody could use it for its own application. So the difference between us and the others, I would like to say, is that we give complete picture, complete procedure, how to implement your model, how to check it. It's not completely scientific, but people working scientific give a lot of prescriptions. When you try to implement them, you couldn't. So we give the code, we give the link in our papers and check, okay, this is our experiment, please confirm whether you have any objections. This is about the gates, reconfigurable filters, you see in many devices. Now I'm going to neural networks, which is maybe, I skip this because it's more or less convenient. Everything could be checked. And to prove that memory store doing its work. About the neural network, memory stores could be used on, especially to replace synapses. How it works, so we did intensive literature review and find out how they are using. The main disadvantage when we use one memory store as a synapse is that we could not realize negative weights. You know, the synaptic weight in neural networks could be positive and negative. If we use one memory store, we could not realize negative weight. There are many people that give different tricks, so we did also with two memory stores one can use can obtain negative weights. With such as schematics, this is our implementation of this neural network with using memory store crossbar, used for some of memory stores are used for this weights, the other for the next neuron. So especially memory stores are taken from memory store matrix. Every cross point is a memory store, and implement here to the corresponding schematic. Now I have a chance to have such a board in my lab and to doing experiments with real memory stores to compare the behavior. Still, because this is not ours, we have a lot of problems with them. Yanislav could tell this because he is involved in these measurements. But anyhow, our plan is to compare the results. So again, a lot of things about the memory store synapses. But once again, the authors do not present complete schemes. Electronic schemes of the corresponding synapse and the corresponding neuron and the corresponding neural network. On every level, what we did, we present a schematic. We did a simulation, we did present comparison of simulated and results and results with MATLAB, for example. These are papers that prepared for this. We started with two memory store synapse, but two memory store synapse is not good. So this was 5 years ago. This is the history how we started with synapses. But so this is maybe the last slides how we proceed. This is a basic neuron. What we did, use memory store for positive and negative weights. We used two apps, one for negative to reverse the signal for the negative weights, and then we use, this is the transfer function. At this level, transfer function is modeled with a dependent voltage source. But step by step, we also made a schematic of this. So if we use this structure that works, we have exactly the value of memory stores. These are the coefficients that determine the output of this neuron. So we have, for every input, we have memory store, then one memory store into feedback, and for the neuron we have one voltage source to represent this activation function of the neuron. This is the LT-SPICE schematic of this neuron. So this is the main schematic, this is the electric schematic, this is the LT-SPICE realization. So the disadvantage here is that we use this voltage dependent source. So this is not schematic, this is model. What we did, we developed a simple circuit with 2 MOS transistors and 1 memristors. That is the input-output characteristic resemble the characteristic of the transfer function of the neuron. So with this schematic, we have complete scheme of neural network that we publish. This is our last publication. And what we did first, 3 neurons, 2 in one layer, 1 in the second layer. Very simple schematic. And step by step, we did simulation in MATLAB and simulation in SPICE. And see, the results are very, 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 very close. So our models that simulate the neural network in LT-SPICE environment give the same results like MATLAB, who is the high-level simulator. This is the LT-SPICE general model. These are the neurons. See now the complete schematic. See the transfer functions and 2 neurons. So this one, and this one for the 3 neurons. Of course, we need one more circuitry here in order to, because there is one problem, in order to these output signals of this neuron should are inputs for the next one. But in order to work as a resistors, we need the level to be below the activation threshold. So we need this schematic to reduce the level of output signals proportionally in order to work these memristors to work as a resistors. Otherwise, they'll switch. So these are some tricks that we succeeded to make our application into a neural network. So we have complete application neural network. And these are the results in the voltage that confirms the coincidence of the results with MATLAB. As a conclusion of my talk, I can say that I presented basic historical information about memristors and their properties, and also I talk about some models, classical and modified, did a review of main publications for neural network and memory crossbars. In fact, I did not make it here, only show you, but it is done. Complete implementation of memristor-based neural networks, memory arrays, logical gates, reconfigurable electronic circuits and devices in LT-SPICE. So I presented such schematics in LT-SPICE working in GitHub. And analysis of this circuit show the good coincidence of the results with the high-level simulator MATLAB. So this was all. This is the references. Maybe useless here, but simply I put them. Thank you for your time.
Thank you, Professor Mladenov, for your interesting talk. Now the audience have the possibility to ask questions to the presenter. And may I start?
Please.
Maybe I have not understood correctly, but you said that when we reverse the voltage,
yes,
the resistance becomes infinite.
No, not infinite. R off.
R off. But after that, on the volt-ampere characteristics, there are characteristics in both quadrants.
Yes.
So this means that when we apply negative voltage, again the resistance will be changed.
No, the resistance, the current is negative, voltage is negative, but the resistance is positive.
Okay. Then I can offer maybe your group, maybe my young colleagues Bobby Bonev and Mitko Badarov to try to model an analog memory or the sample and hold circuit using memristor instead of the capacitor.
I'm open for every collaboration. And it is good because we could make comparison.
I tend to do the same, basically. Professor
He's working.
But we can join effort.
Okay,
it's interesting because
I think that it could be a fruitful area for research to make a new application, analog memory using memristor.
Yes, and the main advantage is the very miniature size of a memristor, because the capacitance is proportional to the.
Not only this. The leakage currents of the capacitor will be omitted using memristor.
Low currents, low noises, low level of noises, a lot of advantages.
The primary disadvantage is the lower working frequency of a memristor.
Yes.
Compared to a capacitor, but it can hold much more.
Okay,
Information.
I think there is a good field for research. Bobby, am I right?
Professor Yakimov, please a chance for one question, two questions.
Please.
How about the aspect of compact modeling? Are your models applicable, because the design software in fact works with compact models, and maybe previous, what is the software environment in which you can implement your models?
They implement in AutoSpice, but they can implement in every SPICE application.
Okay.
We
So
didn't try to extend it, but I'm convinced that if it works in SPICE, it will work in every.
Yeah, it could be. Yeah.
Yes, it could.
Yeah. And did you try it for some real world, let's say, design efforts? Did you come up with a compact model or not?
No. No,
Okay,
in
so
fact, I do not have such a
Professor
simulator.
Yakimov, this is the task for the guys. To develop a compact model.
This will be very good, because we have now some background, and this will continue.
Yeah, because it has a lot of opportunities for future applications. So if we would like to push a bit higher than the research, we should aim at developing compact models that could be implemented in design software, and to see how they match with some real world applications, some real devices.
And what we are trying to do now is to by ourselves to have a real device based on our memristor matrix and based on another analog circuitry. So they are not on the same chip, but to make the device on both chips. Then we may design a chip with memristors, but this is done already, so people have it. Our advantage is that we are working on this and have good models. He's impatient.
Yes, okay. Another question.
Developing Professor Mladenov Mitko-Nikolov now is leading two teams with other focus, but based on
many thanks. I guess now young people. I'll be glad to.
He's silent. This is good.
I know.
Okay, another question to the presenter.
Just one question. How compatible is the memristor with the regular CMOS process?
Told you. Metal oxide memristors. Compatible. Yeah. Completely compatible. Yeah. On the same substrate, we can build both semiconductor and memristor device.
Okay, I missed that.
No, this is the basic advantage. So because you can design convenient circuit together with memristors. This is the main advantage of memristors.
Do you know any PDK that has that implemented?
I know, but nobody gives some details. So we try to model all these things, to find some schematics, some results. No, they give the results. They show this is true. We couldn't confirm, and everybody keeps it. The company keeps this in secret. But what we are doing is trying to do by ourselves.
What companies are most active in this area? From the mainstream companies.
The mainstream company is Neuromorphic Europe. Neuromorphic Europe is trying to do this, and they give us some chips, and we continue to work with them. But HP is from the mainstream is HP. HP is trying to do a memory. I guess they have memory.
Toshiba, no, you don't know.
I don't know, but I know that because of military applications, this is closed.
Because Renaissance took Toshiba and maybe they also have something, but
I guess they have. I do not now go into details what the company is doing. I'm doing a little bit more theory, but what we are going to do together, if the young colleagues join to our efforts somehow, we try to find a way to apply for projects for it.
Yeah.
Because this is top of the way. Especially for neural networks or for memories, it's proven that memories based on memristors is the future.
Okay. So let's wish next year to start the conference with a project that is already successful in this area.
With help of everybody.
Okay.
Two questions. First, thank you for the presentation. My interest is on the last part of the memory, but the neural network that you showed us.
Yes.
Theoretical simulation. How trivial it is to be implemented on actual chip? How trivial it is?
Very trivial. It's very trivial to implement on chip. I didn't make it. We didn't make it. We suppose at least. We suppose. But there is no, I don't find some specifics that could make a problem. Probably matching the levels between different neurons, because we have to reduce the voltage in order to work in the other mode under activation threshold. Probably this could be a problem. But we find a way, theoretically, how to do automatically. Do not calculate what will be the voltage to work under the threshold. We find the maximum value that should be below it, theoretically. Matching the levels.
Okay. Another questions? Let's thank again Professor Moda. Are there? Okay.
Thank you for the lecture first. I have one question. How long does last this effect of memristors?
What effect?
Let's say the memory.
Can last forever if the memory, so because it's non-volatile memristor is non-volatile device. Once the memristance is fixed, and if you work below the activation threshold, yes, the resistance of this memristor stays the same.
Thank you.
Okay, thank you again, Professor Mladenov.
Thank you.
The questions can continue at the restaurant. Now, the second invited talk will be given by Professor Tim Peiche from Nottingham Trent University, United Kingdom. The lecture is entitled Connectivity in Connected and Autonomous Vehicles. Let me introduce Professor Peiche. He is a graduate of the Technical University of Sofia, for those who don't know this. But Dr. Tim Peiche is Associated Professor in Wireless, Mobile and Pervasive Computing at Nottingham Trent University, United Kingdom. His research interests are in ICT for ITS and include connectivity for connected and autonomous vehicles, traffic simulation, modeling, traffic telematics, mathematical modeling of the uncertainties in traffic modeling, distributed computing environments, shared memory design domain, ad hoc wireless networks, building wireless communication models for future traffic information systems, telematics technology application in the urban traffic control. Dr. Peiche's primary interest is in novel algorithms for collaborative identification of traffic conditions through ad hoc network wireless communications and building new generation of traffic control systems based on collaborative interaction between all cars. He is experienced in real-time traffic simulation in distributed environment, various platforms, telecommunication, mobile handheld computers used in traffic environment, real-time traffic control systems, programming in C++, cross-platform iOS, OS X, Windows, Unix, and ePOC for PSI on handheld computers, TCP/IP programming, Java, SMS, small message services for GSM networks, WAP, ad hoc networks, Wi-Fi installation and design, G2ME GPRS experience. He has worked on Horizon 2020 research projects totaling 35 million euro and has had numerous successful PhD students. Past president and current treasurer for the European Council for Simulation and Modeling. Please, Professor Page, you have the floor.
Thank you very much. First, my thanks to the organizers, Deputy Minister, and Mr. Lecturer. Thank you for inviting me to give this lecture. By trade, I'm a computer scientist. So, in my talk, necessarily I may slip a little bit into technical details as far as computing is concerned and networking is concerned, because networking is my main major. However, if you want me to elaborate on something, please let me know, and I will do. In my work, I cross the boundary between computing and traffic management, connected vehicle connectivity, networking between connected vehicles, and so on. So I'll be talking about all these domains without making a difference between one or another. However, again, stop me at any point if you want me to elaborate on any of the topics. So without further ado, let me move on. And that's the agenda that I'm going to talk about today. First, what we aim to achieve. I will show you a short video, and it's funny, the video, hopefully, for everybody. That is what we want to achieve. Maybe not to the degree shown in the video, but nevertheless illustrates the point. Then we will go into some standards. We will look into US and Europe standards for developing intelligent transportation systems, or ITS. We'll look into some use cases for building car-to-car and car-to infrastructure communication systems, for short C2C and C2I, car-to-car, car-to infrastructure, altogether C2X, meaning car-to-anything. Then we will look into the Wi-Fi 802.11p standard, which is the Wi-Fi standard for connecting between the vehicles. And some of the algorithms that I'm looking into and in my research group. Then we'll have a look ahead, what possibly could come, and then I will be open for questions. So first of all, some visualization of the networking worldwide. It looks like if we can have a visual link between networking devices, we'll have something like that. A big chunk of this is down to mobile cars, any mobile vehicles. So my aim here is to make sense out of it. What can we do to make sure that we achieve the aims, to use all this network connectivity to achieve the aims that we want to achieve? And these are the research questions that I'm asking in my research work. How to make sense from all that networking, all this networking data, nodes, and so on, and how to build effectively a mobile network for benefit of all the cars moving. What are the rules for communicating in such an environment? Can we have algorithms which to deploy in all these moving vehicles, and they should be able to generate this effect, algorithms should be able to generate new knowledge and detect new traffic conditions. Distributed nodes entertainment is also a big deal of it. I tend not to look, or less to look into this. And security, again, although very important part, opening the bracket here, just imagine in the current situation where you have autonomous car, that somebody is able to generate artificial traffic lights in front of you, to project into the car without having actual traffic lights, but to project information in the car that there is a traffic light showing for you to go left and then right, and then you can drive the car wherever you want by essentially braking in the car. So security is of utmost importance. So I want to show you this video. Can you start the video if you... Let's see what we want to achieve. Well, there is a music, but I can't sing, so you'll forgive me here. Okay, so what we want to achieve by communicating between the vehicles, pedestrian vehicles and motorcycles, everything, we want to achieve a high throughput. If you can go back to the video? No, not to the video, to the presentation. Okay. So we want to communicate between the vehicles, between all participants in the traffic, so that by the virtue of exchanging data about the state of the vehicle, about the speed, about the direction, and so on, having some optimization, having some analysis, and having some identification of traffic conditions and everything else that comes to mind, not excluding the central traffic control, not excluding the legal matter that is involved here, and so on, to achieve the maximum throughput in our network, in our road networks. That is the idea. So my part of it is to come up with new algorithms, which on the basis of networking, to go some way towards this aim. And now what I'm going to present to you is some of the challenges first that we face when trying to achieve this aim. What are some of the characteristics of the networks that we are having to deal with, so that at the end of the day we can come up with something meaningful that we can then implement in the cars, and especially in the upcoming autonomous vehicles. Maybe some of it will be implemented even in non-autonomous vehicles, depending, so that we can go towards this. So the first thing to highlight here is that we have very unstable neighborhoods, meaning that as the cars move, they form and they break links between themselves, speaking from networking point of view. So this is illustration where you have 1, 2, 3, 4, 5 situations, and these are the cars at the top going to the left, at the bottom of each square or rectangle going to the right. And as they go, they form new links, as it is the case between the red car and the green car here, a new link compared to time number 1. No new links here, there are other links here and here. Now this link here to the green car disappears, and we have this remaining, that remaining, and so on. I don't need to explain in very big detail. It's very clear from the picture that the links between the vehicles appear and disappear as the cars move, and because of that, we need to anticipate this in the algorithms, and we need to take into account. So, what are other characteristics? Dynamic networks, because of these highly unstable neighborhoods. Mobility patterns dependency. We look into the direction of move so that we can form a network, possibly a platoon on vehicles which are moving in the same direction with the same speed and so on. Irregularity, you can have big variations from one day to another, maybe dependence on the day of the week, maybe dependence on the day of the month, maybe the day of the year. We also are looking, I have one upcoming paper together with a colleague of mine to look into social media to anticipate traffic demand, meaning we look into the publications on the social media to try to anticipate what people are going to do and try to avoid congestions, and this is on the side of traffic control, city traffic control. Global knowledge assumed, this is also something very interesting as a problem in theoretical aspect. Everybody is simulating cars as if they know what they are going to do, big brother knowledge about the cars, and then simulation. However, this is not the case. What my students are usually doing is to have a simulation of the cars, then a simulation of the networking between the cars, and then another step to generate the knowledge about the simulation and to come up with new algorithms. Now we are going a little bit geeky here. The 7-layer transport model, this is networking. For those people who are close to networking, all networking, all networking is divided into 7 layers, where the first 3 are the top layers. And the impact of what I'm talking about is impacting on the lower 4 layers, which are computing, so to say, highly computing related layers, while these are application layers at the top. Now, what we have here is the American model. There is a difference between the American and European model for managing the traffic architecture for communication. In the American model, we have a fixed point communication here. We have entirely mobile. We have roadside infrastructure. So you will see, if you read literature about car-to-car and car-to infrastructure communication, that there is onboard unit and there is roadside infrastructure unit. So these are 2 different units, although they communicate on the same level. And then we have standard networking management centers, let's call it this way. Authorities management centers where you have traffic management and so on and so on. So the point here that I want to make is that vehicle to vehicle is a big chunk, in fact 1/3 of the whole networking that takes place in the traffic environment. So my research and what I want to do is to stay here in vehicle to vehicle mainly, possibly from time to time with the help of roadside infrastructure, to generate new knowledge, to employ algorithms which can deliver networks in the cars, and then this to benefit for the final aim that we just saw, this living of the vehicles when crossing intersection, in other words, maximizing the capacity. The next slide. The next slide is European architecture. So, as you can see, quite simplified in comparison with the American one, but I want to make one remark here, and this is about CAM basic service. This is car message service, and this car message service means that the autonomous cars nowadays are required to have a every 10 milliseconds a message which to transmit car status message effectively. And this transmission of car state, broadcasting of car status messages, then to be piggybacked with these algorithms, with information about these algorithms, which to look into these messages, and then these messages to be, this information to be processed in order to make sense out of the cars. Now, I like to say that what we are trying to achieve is not something in the cloud, because the cloud is yet another remote server. We are working towards something that is in the midst, meaning that we have something that is in the virtual space between all the cars. We are trying to achieve something that is in the virtual space between the cars. And this virtual space between the cars exists only if there are cars on the road and communication between them. If there is no car, there is no simulation in the midst, there is no need for control. Okay, so this car message here is essential in achieving this. This is more detailed European architecture representation, and as you can see here, for more computing-oriented people, TCP/IP, UDP, and all this stuff that is highly technical and highly network independent. On the left-hand side, management permeates everything, and on the right-hand side, security permeates everything. So you can see that security and management are indispensable in this work. And on my side, I can say that I had to become quite acquainted with traffic management, so that from the algorithms I can relate to the traffic management centers and local authorities. And in my work, I work with a lot of local authorities, so that these algorithms that I'm trying to prepare are useful. In the communication, the most useful way to communicate between the cars is the so-called DSRC, or Dedicated Short-Range Communication. This is a short to medium-range communication for intelligent transportation systems. And DSRC is a vehicle communication to from proximate device on peer-to-peer basis without intermediary. I take it that everybody here knows what peer-to-peer networking is. I don't need to explain this. Everybody has used peer-to-peer networking to connect a tablet to their mobile phones, so that from the tablet they can access the internet. So that is similar technology. Except that this DSRC is based on 802.11p, which I'll be talking about shortly. And using it is very beneficial for building such applications. So maybe it's a little bit overbearing, but we'll look very quickly into special cases which are identified by people working in the area of traffic management, so that these cases, through the help of this DSRC, can deliver the results, can deliver what we want to achieve. So we have forward collision avoidance, emergency repair, but we will look into each one of these cases, not each one, but most of it. So the first one, forward collision warning. It's very obvious. We have stopped car, and if we have a DSRC communication, that we can warn every approaching car that something is not quite right, so that they can take evasive actions. Opening a bracket, I take it that everybody is specialist in driving, so any advice is welcome here. So, next one. Traffic jam. You can see here why this is useful, because the field of vision of this car is not it's not great. It is blocked by a big lorry in front of it. So this one is braking hard, and relating this information to the car behind would be very beneficial. What I want to say here is that one of the algorithms that one of my students has developed is about information which is spread around all the cars so that to identify the boundaries of a congestion, for example. So this is one example how this DSLC could be beneficial to identify the boundaries of the congestion. And this warning is a little bit late. Brake lights, emergency brake. This is emergency brake, but apart from emergency brake, this DSLC could be helpful to generate the information about the boundaries of the congestion so that advanced warning, not emergency warning, about brake lights could be achieved. Blind spot warning. Everybody knows that from time to time we are just sleeping at the wheel almost and couldn't or didn't notice a car that is next to us and simply took the wrong turn and almost hit another car. And of course got a healthy dose of sound. Do not pass warning. Again, notice that in many cases we have the car with field of vision. So these are mainly cases where we have limited vision for the vehicles, and we can help with this limited vision by delivering the information from a vehicle which has normal field of vision. Forward collision warning. Again, we have two cars moving. If they are not careful, they make a line. But having information about the surroundings helps. So that was car-to-car direct. Now we can have car-to-infrastructure in order to help car-to-car communication. And we have red light running, left turn assist, right turn assist, and so on. Application enabled by signal request message. In the interest of truth, we here in Sofia we have a little bit of that, because on the traffic lights you can see how many seconds you have for change of light and so on. But this would be even more beneficial if you can have it on the dashboard. So the idea here is through VSIC, or Vehicle to Infrastructure Communication, to have this information. And as you can see here, this is called SCAT, and this is for signal phase and transition acronym. So that we have all this information transferred into the car directly rather than have it somewhere outside. And then we have other possibilities. So this is illustration of the information that we have again. So we have green wave applications where this signal phase, this is when we have switched to green, switched to red. Opening a bracket here, in UK, we have for the first time, and then this split around in other countries, similar systems. For the first time about 30, 35, 40 years ago, a system which controls the traffic lights by measuring the number of cars, not strictly speaking the two, but with a degree of confidence you can say that. The number of cars, measuring the number of cars approaching a crossroad, then optimizing all this, and then deciding how much green light each direction should take. It is called SCOOT, and I have, during the years, become quite well acquainted with how the SCOOT works. So based on that information and based on the information inside the cars, we can improve that, because it's very expensive to dig the road and to have inductive loops in the road. But they are augmented now with visual. Some of my students have done visual optimization of the crossing of the traffic crossings on a crossroad based on visual application which counts the cars. So anyway, not just visual but also crowdsourcing will come to that. It's called floating car data. Will help in this way. Work zone warning, you can see here, it's self-explanatory that we have some part of the road blocked, which is very often the case here on the motorways, for example. Very useful in that case, where you have a advanced warning for this. Hazardous conditions ahead, another case, another use case scenario where you can have useful information, where you can be warned up to maybe half a kilometer in advance. Preempt, also used for transit freight priority. Preemptive control means that we can have the traffic lights in such a way, controlled in such a way that to give advantage to public transport, to emergency vehicles, to any other vehicles that need to be prioritized in front of the normal traffic. So all this can be achieved through communication between the cars, and the drivers can be warned rather than rely on their visual to hear the sirens and to hear the sound and to take measures. Tolls, I understand here that there are people looking into tolls, and there are some applications, there are some projects here with some people, for example, Professor Spasov from Plovdiv. They are doing similar work here, and these tolls can be augmented with information about anything that is sent directly to the cars. And I don't know if there is such information at the moment, but in any case, this is a possibility. Rail crossing, we can have again the same warnings, the same information given to the cars. And again, we can have, it's not, can you see here these lines? This should have been a circle in pink, and this should have been a circle in pink, but it cannot be seen here on the computer very well. So imagine that we have two circles, two overlapping circles, each circle representing a given communication area. So this given communication area in the middle here, so the circle, one circle is like that, and the other circle is like that. So in between, you can see here, overlapping area. And this is area where communication signals clash with each other. So we have to be careful when designing such systems, not to overlap the clash between communication systems. Now we are going to have a look at the technology behind it, and the technology behind it is 802.11p. This is a technology which again differs between US understanding of the technology and Europe understanding of the technology. We're going to have a look quickly at that. So this is dedicated short-range communication, DSRC. The standard is given here, and although there is a standard, still there are differences. So this is the US version of it, and this is a service channel. This is the whole range of all channels within 802.11p. So we have 1, 2, 3, 4, 5, 6, 7, 8 channels, and each one of these channels is dedicated in some way. And we will look into some of the dedications of the channels. So this is Wi-Fi, but not like this is the same range as Wi-Fi, normal Wi-Fi, but in a different way maintained. So this is a special service which is dedicated to basic safety message for vehicle to vehicle. This BSM, or basic safety message, as I said, is generated every 100 milliseconds, 10 times in a second. And this could be used for, I'm here, distributing information like I'm here, that's my speed, that's where I want to go, and also of this, or that's what I'm experiencing, like a problem or not a problem, and so on. And this safety messages could be augmented so that with the augmented information you can deliver your own. And there are devices. I specifically use Corda Wireless, which is a company in Australia which manufactures these devices and maintains the standards. So this is a channel for basic safety, for map message. This is for geometry, vehicle to infrastructure, so that the infrastructure delivers geometry of the traffic lights or the streets and everything else to the vehicle, and signal phase and timing message, these seconds to the end of the green light or to the end of the red light to be delivered into the vehicle. So the next channel dedicated is for high power long distance communications, intersection collision applications, and so on. And there is a control channel here, which control channel controls this one and that one and that one and that one, so that applications can use the control channel for service, for providing the service through these 4 channels. So this is analogy, I can make analogy with the SIP service, Session Initiation Protocol, if you know what it is. This is a digital telephony where you have a control channel, and then the information between the 2 digital phones go through directly, peer-to-peer, but the communication channels, this communication channel peer-to-peer is controlled by a server through control channel. So that's something similar could be done here. And this is the Europe standard, where you have a different dedication of all the channels, and it is at the moment much less used than the American way of structuring. But nevertheless, if European applications take off, then might that be the standard, so you never know. Anyway, there is American US prepared connected vehicle reference implementation architecture. This is a reference implementation. I want to emphasize here a reference implementation, meaning that we have something that we can step on and use it, develop our own stuff as we need. And developers, deployers can use this reference implementation for experimentation and so on. I guess I haven't come to this point, but I guess for commercial use, it will have to be some royalties. Okay, and this is a comparison between the reference implementation model. That's the 7-layer model that we have. That's European ITS reference architecture, and this is yet another networking and TCP/IP framework networking architecture. So this is for comparison. I'm not going to go through it. It is quite probably boring for everybody to do that, and there is not much point. It is a reference comparison rather than anything else. And I want to say a few words about floating car data. Floating car data is a way of using all the cars, all the vehicles in the road to collect data, which is Google doing. However, Google is doing it for its own purposes and for charging you for using it. I have done some work for a company with autonomous vehicle through Google, and it's quite expensive as well, because they wanted to do some optimization of a fleet of autonomous network vehicles, and to deliver a service like taxi on call, something like that. And to do the optimization on the basis of this, they decided they don't want it. So floating car data is something that can be utilized by local authorities through application, for example, which to provide authentication. I don't have such application. I'm interested in building one. To create local authorities to have application, as you drive, for example, into a city, then this application comes into your car and you become part of the transport movement and control in this city. And then you are authenticated in an appropriate way, for example, through blockchain technology, what I'm interested in using for this authentication. And then, based on optimization, run either between the cars in the mist, as we mentioned, or between all the cars globally in the city, so that we can have a better, remember the first video that we saw. Simulated connectivity, that's one of my students' simulations in Nottingham, how the cars connect in Nottingham, and then running simulations and optimization on the basis of this connectivity. And this connectivity, what we looked into was how much cars we need for best connectivity. So there is an optimum between the number of cars and the connectivity that we want to achieve, the speed of communication between the cars. Because too many cars, if there is no car, there is no communication. So no good communication. If there are too many clashes between the transmissions, not good again. So there is optimum inside between these two. And we looked into a correlation between how many cars there is in the street and how good the communication between these cars had. So this is a map not on the congestion, this is a map for communication map. Generally there is a reverse connection between congestion and good communication. Another of my students looked into this information that we are distributing. What does it relate to? So windscreen wipers relate to rainy conditions, rainy conditions. ABS system relates to slippery road, reduced speed also relates to slippery road, brake light, foggy, fog light on the car, having a fog light, foggy condition, and so on. So we are looking into sensors in the car to identify possible conditions on the road. And how many of those cars we should consider to trigger the warning is a question that needs answering. How many of these should be activated to trigger warning? Again, another question that needs answering. So these are all algorithms that needs first creation and second further implementation. Looking ahead, there are 5 trends identified in developing the vehicle fleet. And first is personalization. We like our car to be as personalized as you personalize your computer, very much. Well, I'll open another bracket here. As a joke, when I presented my work at the university, my joke was that we have developed a phone and then we put wheels on the phone and on the computer and then we start driving our computers around. So basically, modern BMW is having in the region of 90 processors, 90 different processors in it at the moment. Modern car is having more lines of code than Apple module going to the moon. So we are not only computerizing our vehicles, but we are also personalizing it so that you have personal key. When your key, you open the car with your key, then the car sets up the car in the way, moves the seat, puts the mirrors in appropriate position, and so on, according to you, or for example, according to the second key, which is your wife's key, and it is a different setting. Algorithm-based everything. More and more in the car, you have lines of code, processors, and therefore algorithms. And you probably have heard about the cars having a network CAN bus called. Have you heard? Do you know about CAN bus? Do you know? Yeah. So the CAN bus is something that you can use to deliver software information, software commands to any part of the car, or to inquire about the state of the car. And again, as a matter of joke, my colleagues from BT, when we had a project, and my colleagues from BT playing with this managed to stop the car in the middle of the motorway, so that wasn't a good idea. Anyway, everything is based on algorithms, and everything nowadays what you do is some sort of algorithm in the car. Dynamic active data collection. This is extension of what I mentioned, floating car data. Floating car data meaning that the cars collect data as they move. So crowdsourcing of data, if you want to call it this way. And all vehicles will have to collect the data and make use of the data not only collected by their vehicle, by the vehicle itself, but also neighborhood vehicles. Safety, I cannot overemphasize this, but it's not my area that I'm working on. Safety is big chunk of work nowadays. And networking is what I'm looking into, and this networking permeates everything else, really. So, again, what to do to make sense out of all this. So, thank you for your attention. That's all I wanted to say.
Thank you, Professor Pechev. Now, you have the possibility to ask the presenter.
Thank you for the presentation. I would like to ask, what's the range of this proposed peer-to-peer activity?
What's the range of communication?
In terms of meters, yes.
Up to 350 meters.
So it's not only with the nearest car, it's more wider.
Yes, but you are running the danger. Okay. Nowadays, low-cost GPS gives you location with precision 10 to 20 meters, low cost. High cost, several thousand pounds, devices can give you 10 centimeters precision of your location. Now, something in between probably will cost less, but again, you get what you pay for. Some of the algorithms rely on hopefully better location than the very simple ones, so that you can distinguish this basic safety message that I mentioned. When you transmit it, if you have 10 centimeters, you will know where it comes from, the direction it comes from, because you have GPS in the message. You may have, if you want, depending on the algorithm. So up to this 300 meters, you will know every car along the way retransmitting the message. You will have know whether this car is moving or not, staying in congestion or not, having slippery conditions or not. Whatever you want, basically. So up to 300 meters is, I need to mention here, there is this canyon effect. Do you know what canyon effect is? Tall buildings in the city may prevent you from transmitting the message properly, or may distort the message because there will be reflections from the buildings. So this canyon effect will disturb you or prevent you from getting good GPS signal. Again, you have reflections of the GPS signal. Inside tall buildings or inside tunnels, for example, you cannot get proper GPS signal. Again, if you have GPS, again, it's wireless communication. Again, you may have distortions with the canyon effect. 350 meters unimpeded by obstacles. Way or go.
I've seen security is embedded into the standard, probably because of malicious parties and other attacks. Can you tell us what's the most common attacks that are being analyzed against those types of networks?
I'm not expert in security. From what I know, from what I have heard, most people are afraid of the software when they are to put artificial obstacles, virtual obstacles in front of the car to make the car go wherever they want. First. Second is to burn the car down for, I don't know, get some malicious code to destroy some of the processors. Anything computerized is prone to this. What else? Of course, you can crash the car. So these are the most common things that people are afraid of. But because it's computerized everything, they are no different from standard computerized threats. Of course, the end result could be different because you have a moving code.
Are there any mitigations that are being taken in the standard for removing?
Every standard tries to do this. Every standard tries to do this.
But it was more on a higher level, not just on protocol level. It's more of analyzing, like statistical analyzing that you are getting conflicting messages from 5 cars, and one of them is saying something completely different than the other.
There is this method. Other people have tried authentication methods, so you know who is sending this message, you know who is the faulty party if something happens, and on that basis you need to have somebody responsible for that. So that's another way of doing it. But people have tried in the past, and this is, I think, a good way, a good project to develop authentication framework for autonomous vehicles, so that everybody knows who that is. And I'm trying to do this on the basis of blockchain technology nowadays.
Yeah. Probably somebody sending a message, then other verifying and signing it. Yeah, that's correct.
Okay. Professor Model.
So, for me, it's interesting. You said about the system for control of traffic lights.
Yeah.
You said that it existed 30 years ago, and the control depends on counting the number of cars in different streets. My question is, first question is, whether they count what's happening on the next traffic light, otherwise green wave is...
Yeah. Now, just a quick explanation on that. The system is called SCOOT, which stands for split, cycle, and offset. Split is the how much green, how much red in one cycle. Cycle is the length of the cycle, 1 minute or 2 minutes or minute and a half, the whole cycle, red plus green. And offset is how much seconds you should have before the green light on the next traffic light starts. So that's for green wave.
So count the traffic lights, but then it became network problem because next traffic light also count the next one, and it was...
It's optimization process.
Exactly. And now the question is whether they count now the information that you communicate, whether traffic lights get this information between the cars in order to better...
I tried to make a contact with these people, providing that it's a commercial system, and they are very reluctant to change it.
But this is the future problem. If everything communicates, why not to communicate with the traffic?
I've been trying to come up with somebody, or try to find somebody that would be interested in this. No.
Thank you. Thank you.
Thank you for the interesting presentation. I just have one question. What do you think will be the potential impact about the urban mobility? And we were just discussing about the optimization problem. Then you said you showed some simulations. Do you think that some kind of a new pattern of urban traffic and mobility would to emerge from this optimization and this optimization problem, communication between the infrastructure?
One of the aims is to take the driver out of the equation, so there is no human being. So the autonomous cars are part of the solution in my view, because then you'll be able to control them and to optimize them and to make sure that the whole process goes as smoothly as possible. So that's the idea. Now, how this is going to pan out, no idea. A lot of studies nowadays how normal drivers would react on
that was my next
cars.
question. Yeah.
A lot of studies nowadays. There is no definite answer to this at the moment.
Some principle also question. You were talking about that when the cars are moving, they, let's say, broadcast where they are going, right?
Yeah.
The route.
But they're no, not the route. They're going to, they're broadcasting the direction of move.
Ah, only the direction. Okay.
Yeah, privacy issues, you mean?
Yeah, because not usually you don't travel, especially on day-to-day basis, setting up a route. You're just driving on your own. This means that you cannot.
Of course, you can do that if you want. You can share your route anonymized, which is the way everybody is doing it nowadays. Yeah. You can anonymize it and say there is a car going from A to B. Who is in the car, or what is the number of the car? And this anonymization is taking part even nowadays when collecting traffic data, because a lot of research goes on in the city where you go from and where you go to, so that the optimization can take place beforehand. And then when you do that, you necessarily record the number of the car, because you need to know that this car you follow to there. But this anonymization should take place if the research is properly conducted. This anonymization should take place. We specifically have, for every project that I've had, specifically had anonymization section, how we are going to deal with privacy.
When the standard is used for intelligent transport system, we assume 100,000 units. So my question is how the verification, the validation will be performed with such a large system?
You need good computers. As far as I'm concerned, and my research is concerned, we can only do it on a small scale because the computers we have, they are good range PCs, but this is nowhere near enough. We can do something like 100, 200 nodes. So at the moment at Nottingham Trent University, we have a facility which we are trying to put in use. It's still not in use, but some of my colleagues are trying to put it in use, and there are, I think, I can't remember, 256 or 512 machines in a cluster, and we are trying to parallelize all this so that we can increase the optimization process, the scale of the optimization process, and verification for that matter. But we haven't done it so far on such large scale.
Yeah, but you're planning only simulation, but how, if we are going to accept the system a real case scenario, how to test real case scenario.
Well, I agree with you. We need to verify it if we are to accept it on a large scale. But we haven't done it, if that's the question, we haven't done it. Because we don't have enough, powerful enough computers. We may use this as a use case for supercomputer, for example.
In the video you showed in the beginning, not only the cars, but also the pedestrians and the cyclists, everything was seen. So this system, does it consider communication between pedestrians, and bicycles?
Well, the answer is no. And the answer is it could. So if you want to involve everybody, and if you try these pedestrians to move as they say they will move, or they set to move, then why not? But these pedestrians, they will make a step and then say, oh, and then the car will hit them.
My view is more like a warning for the cars that there's pedestrians.
The cars can detect pedestrians.
My guess is that GPS devices will become more and more precise, and then every participant in the traffic wears such a device, then proximity warning could be triggered at every time, and the cars can be stopped at every time. So that's my answer to this. As we move towards automatic detection of obstacles and so on, if everybody is made to wear such a device, then even the cars will be able to do preventive measures. Now, the cars nowadays don't rely only on GPS devices. They rely on radar, LiDAR, everything else that you can think of, video cameras on the top of the autonomous car to detect pedestrians and everything else. So it's not the only way through this DSRC communication to do that. But the idea behind these algorithms for communication is to make all this happen to the best practical way.
And maybe in the case of pedestrians, there can be a camera that's sending the data instead of the pedestrian sending the
autonomous cars for sure have cameras to detect pedestrians.
I meant the static camera on the...
That as well.
Yeah. On the crosswalk, for example, that there's a
pedestrian. But pedestrian and the drivers as well cannot be trusted. I'd like to think that I'm a driver that can be trusted, but I have done my fair share of traffic situations.
Other questions?
Yeah, it's a small one, and I think you've captured it. But there's this concept of a virtual traffic light when there's some traffic situation, and then hours after that, people are still slowing down because of something that happened hours ago.
Yeah.
Are you attempting to solve this by the flow of the cars? Because the algorithm for solving this is to spread the cars and start moving them with higher and higher constant speed, instead of everybody rushing and then stopping.
Yeah, as I said, the idea is to optimize the traffic demand, as it is called properly. So the traffic demand is there. You need to detect how many cars, where they want to go, and then to make sure through optimization and through reducing the speed or increasing the speed of the participants to achieve maximum throughput. And to achieving maximum throughput, as I like to say, you're saving the planet. So you can, from there, you can deduce the number of stops, fuel consumption, number of the hours the engine is running on the road, and everything else. In other words, you take care of the environment by optimizing the movement. And if there are no other questions, I just would like to say that as of a couple of days, UK is back into Horizon program. So I'm looking for partners. I could bring, obviously not in Tech University into the picture, a couple of city councils from UK. I could bring SME into the picture. So I think we are a good partners to have. So if anybody is interested.
Yeah, it will be interesting. Especially now the British Embassy is quite active with seeking collaboration with us. So if as a follow-up we may, let's say, add some of your areas of expertise and to, how to say, to push things.
I have been part of, was mentioned here, many projects, many European projects before we Brexit.
Yeah.
And I'm keen to jump back onto Horizon project.
Getting to Horizon can be the first step towards joining the EU.
Journey.
We'll stick to it.
Okay, so thank you, Professor Pejčev. And this discussion can also continue in the restaurant. Now, before closing the plenary session, I have some technical notes.